membrane potential changes. So our resting is about -70. And then we can have positive changes which depolarize the membrane potential. And we can have repolarization, which are changes that move us back towards rest. And then beneath our resting membrane potential, we can have hyperpolarizing events that actually take us a little bit more negative than that -70, our resting membrane potential. So depending on the direction of change of the membrane potential, we can classify these as different types of events, right? Depolarization, repolarization, and then hyperpolarization is overshooting, becoming more negative than the resting membrane potential. So in order to describe what happens in order to fire an action potential, we're going to first start by looking at the ion channels that are present on a neuron. So I mentioned earlier that the sodium-potassium pump and the leak channels are two structures that are on the membrane of a neuron, but there's some other things that are here as well. There are leak channels. We talked about those. Those are all over the neuron, so all throughout the length of the neuron. These are always open. These move ions passively according to their gradient. And these, we said, help to establish the resting membrane potential. There are also ligand-gated channels, and ligand-gated channels open or close in response to something binding, something we call a ligand. So any type of molecule or neurotransmitter or ion that binds to this channel will eventually open it or close it. And we have some of those present, specifically on the dendrites and the cell body, so the proximal parts of the neuron. There are also voltage-gated channels. These open or close in response to changes in the membrane potential. So at a different voltage, these channels will do something different. They're going to be responsive to that value of the membrane potential. And specifically, we have sodium voltage-gated channels and potassium voltage-gated channels. And these are the ones that are really involved in the action potential events. These are found mostly throughout the length of the axon, but really heavily concentrated at the axon hillock, which is the neck, so to speak, of the axon, of the neuron. And then finally, there are calcium channels. These are located only at the axon terminal, and these are involved in communicating the signal on one neuron to the adjacent neuron. It's going to be at the distal part of the neuron, and there's going to be release of neurotransmitters down at that end, which will eventually cross the synapse and communicate with an adjacent neuron. Okay, so let's go back to this. Yeah, let's go back to this drawing here and just point out where those concentration of channels were. Okay, so we said at the dendrites we had mainly ligand-gated channels. And these are going to have to be bound by some specific molecule in order to open up. We have those at the dendrites as well as at the soma. These are also ligand-gated. Along the axon, we had voltage-gated channels. And then also heavily concentrated at the axon hillock, we also have voltage-gated channels. All right, and then down at the axon terminal, we have calcium channels here. All right, so we got ligand-gated channels at the proximal part of the neuron, the dendrites and the soma. And then we've got voltage-gated channels throughout the length of the axon, but really concentrated at the axon hillock. And then down at the distal part of the neuron is where we have calcium channels that are involved in that neurotransmitter release. And let's also put a note here that we've got leak channels throughout the length of this neuron. And we already know that there are 25 times more potassium than sodium leak channels. Okay, and those are found all over the neuron. Okay. All right, so understanding where those channels are is going to be really important to understanding the synapse and then eventually how they generate an action potential. Okay. All right, so changes in the membrane potential are controlled by changes in the flow of ions through these channels that we'll speak about. So we talked about sodium being a very, sodium having a very positive equilibrium potential. So if we open up sodium channels, we're going to have a rush of sodium into the cell. Potassium having a negative equilibrium potential. If we open up potassium channels, we're going to have a slow trickle of potassium out of the cell. And so the movement of these ions help to change the membrane potential to be either positive or negative in either way. So potassium has two types of channels. They're the leak channels we talked about, as well as the voltage-gated channels. Now the voltage-gated channels, as I mentioned earlier, are going to open when the membrane potential gets to a certain level, and they're going to close when the membrane potential gets back down to rest. Sodium has mainly voltage-gated channels. Now, I think in your notes you may have only here, and that's not true. So you do have a few leak channels. We spoke about them. They're much less in quantity than potassium, but there are leak channels for sodium as well. Okay? So mainly voltage-gated channels that are going to do a different thing at a different voltage, and then a few leak channels that are helping to establish the resting membrane potential. Okay. All right, so let's speak about what happens with sodium channels first. So these voltage-gated sodium channels open when the membrane potential gets to negative 55. We call negative 55 our threshold value. So when we have enough graded potentials that get us to threshold, then there is a triggering of the opening of this voltage-gated channel, and then sodium can rush into the cell due to its strong electrochemical driving force into the cell. This allows the membrane potential to rapidly climb towards the equilibrium potential of sodium, which we know to be positive 60, right? Very positive. And at positive 30, we have these voltage-gated channels deactivating. So the membrane potential never actually gets to the equilibrium potential for potassium because these voltage-gated channels are triggered to close when the membrane potential gets to positive 30. Okay, so they open up at negative 55, the membrane potential climbs, and then they close at positive 30. Now let's look at the events on this gate that happen to allow this. So this channel actually has two gates. They have an activation gate and an inactivation gate. The activation gate is voltage dependent, so it's going to be open at negative 55 and then closing at rest. It's going to open in a positive feedback way. So when it opens one sodium channel, sodium rushes in through that channel, but that's going to trigger more sodium channels to open up, and then more sodium will enter. And that's an example of positive feedback, right? That potentiation of sodium rushing into the cell. The inactivation gate is going to be a little bit more complicated. It has a voltage and a time-dependent feature. So it's going to open during depolarization, but that is going to also be a signal to close after 1 millisecond, also after depolarization. So I'll say that again here. The inactivation gate is going to be voltage and time sensitive. So at negative 55, it's going to open, but there will also be a timed component here, where after 1 millisecond, it will close as well. So there are two signals being sent at negative 55 millivolts to open and then to close after 1 millisecond.